If you've ever asked an LLM to optimize your code, you've probably seen a familiar pattern. It first looks cleaner, it might even sound smarter, but when you run it, the speedup is inconsistent. Sometimes it's not faster at all, or sometimes it's just plain wrong. This paper makes a simple point that's easy to miss. Code optimization is rarely a one-shot writing task. It's a search problem, and the authors propose a system that treats it that way. Now you see, historically, automated code optimization leaned heavily on rule-based factoring, expert-written rules that target specific inefficiencies. Now, that's labor-intensive and doesn't cover the long tail of performance issues. Most recently, LLM-based approaches treated optimization like sequence generation. Prompt the model, get optimized code back. The authors of this paper argue that this one-step generation paradigm runs into two fundamental limits. One, complex optimizations are combinatorial, meaning that real speedups often come from combining multiple changes, not one clever prompt or rewrite. And two, it's hard to inject the right optimization knowledge precisely in a single prompt. So outputs tend to be under-optimized. So the question becomes, instead of hoping the model nails it in one try, what if we systematically search for better solutions? That's what the paper proposes. SBLLM, a search-based LLM framework for code optimization. Think of it like this. The LLM is your generator of candidate optimizations. But instead of stopping at one output, SBLLM iterates, scoring candidates, selecting the most promising ones, and using them to guide the next round. It follows an evolutionary search loop. Generate, then evaluate, then select, then breed better solutions. Repeat. Yes, you heard me right. I said breed. Now, SBLLM has three components that makes this loop practical. So the first component is execution-based selection. SBLLM runs candidate solutions against test cases and scores each candidate using correctness. Does it pass? Speed up rate. Is it actually faster? Then it selects a small set of representative candidates. It prioritizes correct and fast solutions and also tries to keep them diverse, meaning so that it doesn't actually keep near duplicates. Even incorrect candidates can be included because they can teach the model what not to do. Second, pattern retrieval. Instead of dumping generic optimization tips into the prompt, SBLLM retrieves targeted optimization patterns from a pattern base using both the original slow code and the selected representative candidates. In plain terms, it tries to feed the model the right kind of optimization hints for this code at this moment in the search. The third component is the genetic operator chain of thought. This is where the prompt explicitly tells the model to behave like evolutionary search. That is crossover, combine the best ideas from multiple candidate solutions. Mutation, introduce a new optimization idea guided by retrieved patterns, then generate a new candidate. And SBLLM repeats this loop until it stops improving or until the representative set doesn't change, which signals convergence. So does it actually work? Well, the authors evaluate SBLLM on the Pi dataset covering Python and C++ derived from CodeNet problems with public test cases for feedback and private test cases for evaluation. They compared against multiple prompting baselines across several LLMs, and the key results they report up to 209% improvement in execution efficiency in their evaluation setting. And there's consistent outperformance across the board, as you can see here. Importantly, the headline isn't LLMs are now perfect optimizers. It's wrapping an LLM in a search loop makes it meaningfully more reliable at finding real speedups. So here's the bottom line as I see it. If you're building developer tools or even just trying to apply AI inside your engineering organization, this paper suggests a practical shift. Don't treat optimization as generate once. Treat it as generate many, evaluate, and iterate. Now, that has product consequences. You need execution, infrastructure, and test harnesses. You need guardrails for correctness. Check out this cool paper in the link below in the description, and thank you for watching.